Okay, I'll start. Lecture 2. 2 or 3? 2. No, 3. So what last time we saw what is a semi group, what is a monoid, what is a group, etc. And we also looked at what zeros of a semi group. Then we also saw some standard examples, and we also looked at idempotence, and this was one of the propositions we proved. Every finite semi group has an idempotent. Okay, this is what we did last time. Now let's continue. All right, let's so imagine, let S dot be a semi group, a morphism, a homomorphism. Okay, sometimes we'll call it just morphism, not just sometimes, most often we call it just morphism, from S dot to T plus. Okay, so uh, I have two semigroups. One is called S dot and the other is called T circle. Okay, so dot is the semigroup operation in S, circle is the semigroup operation in T. A homomorphism from S dot to T circle is a function from function h from S to T such that if I have h of A dot B is equal to h of A circle h of B. What does this mean? So if I have, this is S and this is T. Okay, if I have two elements A and B here, and if I take their product, I'll get A dot B. This is their product. Okay, so instead of, now if I find its image in T, this is H of AB, this is H of A, this is H of B. Okay, so if I take their product in this semigroup S and take their image, it is same as taking their image and taking their product in T. That's what this means. Okay, in other words, the operations of S and T are somehow similar. They respect the function. Okay, in other words, the function respects the semigroup operations in the individual semigroups. um, let's see an example. So this is what is a semigroup. This is what a homomorphism. Actually, I should say it's a semigroup homomorphism uh, because they are homomorphism of semigroups. But, But right now it is understood that when I have two semigroups and there is a homomorphism between S dot and T dot, is T circle, it is understood that it's a semigroup homomorphism. Let's take an example. Okay, let's take the alphabet AB. Okay, A is the alphabet AB, and you remember A star is a semigroup. Yeah, and if I have, let's take the semigroup 0 1 and addition modulo 2. Okay, so that means that 0 plus 1 equal to 1 plus 0 equal to 1. 1 plus 1 equal to 0 plus 0 equal to 0. That is the semigroup operation, addition modulo 2. So now if I map, so this one I can call it Z bar 2Z. That's the standard notation. Yeah, the notation is it comes from ring theory, but this is the standard notation we use for this. Okay, so addition modulo n will be Z slash n is Z. So if I have to the addition modulo 2, so if I take a word W and I can map it to, let's take length of W. Okay, so what is this homomorphism? H maps epsilon to 0, A to 1, B to 1, AB to 2, AB to 0 again, A to, I should say A to 0, AB to 0, BA to 0, BB to 0, and so on. That is this function. Okay, now how do I make sure, how do I verify that it is a semi-group morphism? So I have to verify this condition. If I have h of uv is equal to h of u plus h of v, this is what I have to verify, addition modulo 2. Yeah. So if I have a word of, let's say, how do I verify this? If u is of, if u and v are both even length, then h of uv will be even. So here also it will be even. This will be 0 and this will be 0. So 0 plus 0 will be 0. So I have to verify by cases. Yeah. So therefore, this one mapping each word to the length of the word is a morphism of semigroups. Okay, this is actually a monoid. This is also a monoid. But we'll in a short while we'll see what is monoid homomorphism. But, this is a semigroup homomorphism. Can you tell me another more semigroup morphism between these two things? Let's take another. Can you tell me another semigroup morphism between these two guys? Saina? If I map W, let's call this thing phi. If I map W to WA, that means the number of A's in W. Okay. This is also a morphism. Phi is a morphism. Okay. So I hope any doubts? Okay. Now, if M dot and N circle are monoids, so the so right now we these are just semigroup morphisms, but if they are monoids, let be monoids, a function h from m to n is a monoid homomorphism if one the previous condition that it is a semigroup morphism h of a b a dot b is equal to h of a circle h of b for all a b in m. Second, h of 1 m, that means the identity in m should map to h of 1m should map to h of 1n. Sorry, 1n. That means if the morphism maps the identity of m to identity of n. So you can see that these two are actually monoid homomorphism between these two monoids, because here the identity is the empty word, here the identity is 0. So this one maps identity in a star to identity in z slash 2z. Okay, so these are monoid homomorphisms. Okay, so any doubts? Okay, so these are homomorphism between
Sir, I had one question.
now we have a special case if the function,
Sir,
yeah,
so I had a question. Sir, won't the condition two will the condition two not follow from condition one?
it may not follow. Okay,
Okay, okay, okay.
for instance, I imagine I have a semigroup S dot, okay, and I have any semigroup T circle, okay. I can for instance, between any two semigroups there is a homomorphism. Why? Because T is finite. Between any two finite semigroups, there is a homomorphism. Why? Because both of them have idempotent. So T has an idempotent E. Okay, let E be an idempotent S, and you take the function which maps every element X to E. That is a semigroup homomorphism.
Ah,
Okay,
okay, yeah. Right. And that's not taking.
it is not a monoid homomorphism.
Yeah. Okay.
Okay, so special case if, let's imagine, let phi from, so right now I am writing the dot and circle separately, okay, because I have written I wanted to specify what is the operation in each of these monoids, so that's why I wrote them s dot and t circle. Okay, so I wrote h of a dot b is equal to h of a circle h of b. But usually what we do is that we never specify what the, we explicitly don't notate the semigroup operation. We'll just say S is a semigroup or T is a semigroup. And in that case, you will just write h of a b equal to h of a times h of b. So you will never write the semigroup operation. Okay, because you will be all the time dealing with semigroups, and then you don't want to write different symbol for each of the semigroups. Okay, so now onwards, and you will be able to you will understand what does it mean. I mean, h of a times h of t. You know that there is some implicit operation there. That's why you know that it is in t. It is happening in t. Okay, so I'm going to write that phi from S to T. Let phi from S to T is a is a homomorph. Okay. Now the operation of S and T is implicitly understood that S has some operation, T has some operation, and phi of AB is equal to phi of A times phi of B for all AB in S. Okay. Phi is an isomorphism. Phi is an isomorphism if Phi is a bijection between S and T. Okay. So what does this mean? This means I have S and I have T, and I have S and I have T, and S has these elements, T has these elements, and it's a bijection. Phi is a bijection. So it's a one-to-one mapping, one injective and surjective mapping between S and T. And furthermore, if I multiply two elements here, the operations in S and T match. Yeah, that's what homomorphism means. So in other words, S and T are kind of renaming of each other. If I take these elements and I rename each of these elements with the corresponding elements in T, S and T, I will not be able to distinguish. Okay. So up to renaming, these two semigroups are the same. So usually when you talk about different semigroups, you only count objects up to or semigroups up to isomorphism. Okay, you will say up to isomorphism, you will not distinguish objects. You will not distinguish objects which are isomorphic to each other. That's the standard practice. Okay, so let's, for instance, you can say that let's take an example. Okay, so if S is a semigroup, what is S1? What is S1? Last time we introduced this notation.
S with an you're adding an identity to the semi group.
Yeah, adding an identity to semigroup. Okay, so if S is a semigroup, S1 is a monoid. Now, um, by T of S1, so let's say T of, let P be a set. Okay, T of P denotes all transformations on P. What is a transformation? A transformation is nothing but a function on P. Okay, so if P is this set, this is one transformation. You understand what I'm saying? So, these are elements of P, a transformation is a function on P. Okay. So, example. So P, you say P is equal to 1, 2, 3. Then this is a transformation 1, 2, 3, 1, 2, 3 is a function. Now, if I have two transformations, let's say this is alpha. Alpha, and this is another transformation which is beta. Okay, then I can alpha beta, I take the composition, I define a product of two transformations. Okay, So these are two transformations, alpha and beta. Then I define their product to be just composition. Alpha beta is equal to beta composition alpha. Yeah. If I'm talking about alpha and beta functions, so beta composition alpha is what I define to be their product. So what will be this composition? So 1 will go to 1, 2 will go to 1, sorry, and 2 will go to 1. And where will 3 go? 3 will also go to 1. Okay. So, yeah. So then, so that set of transformations are closed under function composition. Closed under function composition. And also it is associative. This, that is also associative. That means if I have three transformations, alpha, beta, and gamma, alpha beta times gamma is same as alpha beta times gamma. Okay, if I have three transformations. Okay. From the transformations on a set, you can actually define something called transformation semigroup. I'm not going there. I just want to show that every semigroup, let's write it as a theorem. Every semigroup is isomorphic to the transformation semigroup isomorphic to a sub semigroup of transformations on S1. Okay. So what am I saying? So I have a semigroup S, and if I take an element A here, and I have transformations on S1. Okay. So these are the elements of S, and I look at the transformations on S1. What is this transformation? I map XA to the function which takes X to XA. Okay. So if I consider the function which maps every element in S1 X to the element XA, X right multiplied by A. So 1 will go to where? Which one? 1 will go to A. A will go to A square, and so on. Okay. I mean, these may not be different elements. I mean, I should write it this way. 1 will go to A will go to A square, B will go to BA, and so on. Okay. This transformation, I am associating every element A in S1 to this transformation. And now I claim that this is this mapping forms an isomorphism. Okay, it's not. I'm forgot to say tell you one thing, which is that if I take exercise, or let's prove it. We'll come back to the proof of this one, but let's take a detour and prove that proposition. Before that, I should introduce what is a subsemigroup of a semigroup. Let S be a semigroup. T subset of S is a subsemigroup if T is closed under the semigroup operation. Okay. For instance, if I have some examples, so let's take uh, let's take the right zero semigroup one, or let's say A B C. Okay, and x dot a is equal to x dot y is equal to y. This is the defining equations for this one. I multiply anything by y, I get y back. So AB will be B, AC will be C, and so on. Okay, right zero semigroup. What are the subsemigroups of right zero semigroup? How many subsemigroups are there? AB is a subsemigroup. Yeah, BC is a subsemigroup. A is a subsemigroup. Yeah, in fact, every subset of a right zero semigroup is a subsemigroup because I multiply anything by anything, I get back that element. Okay, so
it's 11 o'clock.
another example. Let's take alphabet A is equal to AB, and let's consider um, all words ending with A. All words of even length, W mod 2 equal to 0, forms a subsemigroup of A star. Okay. So this is what is a subsemigroup, and what is a submonoid if the identity is also there. Okay, so if S and T are subsemigroups, if S and T are monoids, and I mean if S is a monoid and T is a subset of S, and you say T is a submonoid of the monoid S if T is closed under the monoid operation and T has the identity. Okay. Now there is one distinction, which is that um, if I have S is a subsemigroup and T is S is a semigroup and T is a subsemigroup of S. And what might happen is that T with some idempotent within S can form a monoid. All right. For instance, if I have the set of elements 1a square, okay, 1a square, and with the rule that a dot a square equal to a. Okay, or let me put it this way. A dot a is a square. A dot a square dot a equal to a dot a square equal to a. Okay, if I have this semi group, this monoid, okay, this is actually the monoid you get by taking the z2 bar 2z and adjoining an identity. Yeah, you take the semi group which is addition modulo 2 and adjoin an identity. That is what this semi group is, this monoid is. Now if I consider a square, this one, okay, if I consider this one, this itself is a monoid with A square as the identity. Okay, because A times A square will be A square times A square will be A square times A square will be what? Will be, oh sorry, this is a monoid. Uh, I don't think so. 1 second. This is, yeah, yeah, A square times A square will be A square. Yeah, A square will be A square. So this is a monoid, which is a sub semigroup of this monoid, but it has a different identity. So so my point is that if I to say that T is a submonoid of the monoid S, T and S should have the same identity. But if I want to say, if it so happens that T is a subsemigroup of the monoid S and T has a different identity, in that case you will say T is a monoid in S, submonoid in S, okay, not of S. I think I think such final distinctions we can make later also, but the point is that whenever you want to use a prefix sub for a structure, for instance, sub semigroup or sub monoid or subgroup, etc., you want to say that the existing elements of, pardon, where is this coming from? The identities are preserved. Okay, the identity. So, for instance, T is a submonoid of S if T and S has the same identity. Similarly, is a subgroup of the group S. You want to say that T and S have the same identity. Okay, otherwise, if the identity is not preserved, you will say T is a subsemigroup of S, even though T is a monoid. I think I'm screwing up a lot. Okay. So you understand what is a subsemigroup of a semigroup S. My point was that if S, let's say this, if S to T is a semigroup morphism, let S prime be a sub semigroup of S, then phi of S is a sub semigroup of T. Okay, phi of S will be a sub semigroup of T. That means if I have, this is S, this is T, and phi is a morphism between these two guys. And if I have S prime, then the image of S prime under phi will be a sub semigroup of T. Okay, this is one. Second, if T prime subset of T is a sub semigroup of T, then phi inverse of T prime is a sub semigroup of S. In other words, if this is S, this is T, and phi is a morphism from S to T, and here I have a T prime, which is a sub semigroup of T, then I look at all the image, all the elements in S, which maps to some element in T prime. This is what is phi inverse. Yeah. all the elements here which map to some element in T prime. So then P inverse of T prime is a subsemigroup of S. In other words, the content of this proposition can be summarized as subsemigroups, or let's say this is a general phenomenon in algebra. Substructures are reserved under morphisms and inverse morphisms. Okay, so let's try to prove this. Proof. So I have S and I have T and I have S prime here, which is a subsemigroup of S, and I have a morphism phi. Now, if I want to say that this image, to prove that phi of S prime is a subsemigroup, what should I prove? I should prove that let A, B be in phi of S prime. Okay, so let's take two elements here. Okay, this is the image of phi. So I take two elements A and B here. What should I prove? I should prove that their product is also in phi of S prime. This is what I should prove. I should prove that A times B is in phi of S prime. Now, how do I do that? So since A is in phi of S prime, there exists. So since A and B are in phi of S prime, there exists S1, let's say SA and SB in S such that, in S prime, such that phi of SA equal to A, phi of SB, small, it's underscore B, okay? I mean subscript B. Phi subscript B is B. Yeah, there exist two elements, SA and SB here, which maps to A and B. Now, what will be phi of SA times SB? This will be phi of, because phi is a morphism, phi of SA times phi of SB. And this is nothing but A dot B. Okay. And SA times SB is actually in S prime. It's in S prime. Since S prime is a subsemigroup. Is a subsemigroup. Okay. So therefore, A dot B is equal to phi of SA dot SB is in phi of S prime. Okay. So this is how you prove that the subsemigroup are preserved under morphisms. Now I will leave as an exercise to prove that subsemigroups are preserved under inverse morphisms. Okay, so please do that exercise. I mean, it's not, so it's just applying the definition, nothing more. Okay. All right, so for the moment, I'm going to take that subsemigroups are preserved under morphisms, and inverse of subsemigroups are again subsemigroups. Now, where were we? We were, I wanted to show that every semigroup is isomorphic to a semigroup of transformations. This is what I wanted to prove. Okay. So now I have a semigroup S, and I look at all the transformations. I look at the transformation which is obtained by multiplying an element by A on the right. Okay, element by A on the right. So now this is a morphism from S, and this I call this morphism phi. Yeah, an element phi maps an element to the transformation which is obtained by multiplying each element by A on the right. So this is a morphism from S to all the transformations on S1. Okay. So I have already observed that the set of transformations are closed under function composition, and it is also an associative. So therefore, the set of transformations on a set is actually a semigroup. So all the transformations on a set is a semigroup. So in particular, the transformations on the set S1 is a semigroup. So now what I have shown is that I have a morphism from the set from every semigroup S to the transformation semigroup on S1. Okay. Now here and this map. So and the map is now to prove that it is an isomorphism. What should I prove? I should prove that the mapping is injective. That means if phi of A not equal to phi of B, if A not equal to B. Yeah. If A and B are two different elements, then their transformations are different. But this is given because I have already identity element. So if I look at phi of A, it will map identity element to A. Phi of B will map identity element to B. Any questions? Hello? Is this proof clear?
Yes, it is.
Yeah, I want somebody other than BSc Maths to answer. I
Yes,
know.
it is.
Yeah, but
Yes.
yeah. Okay. And if okay, now there is, I give you another exercise. Okay. If G is a group, G is isomorphic to a subgroup of to a group of all permutations on G. Okay. So what do you mean by permutations on G? You look at every element. You look at the map which takes every element G to the element GA. Okay. This is what so since G is a group, G is also is a semi-group. So you look at the previous the proof which we just concluded. So it maps every element A in G to a set of transformations which takes every element of G to GA. Okay, and you want to say that transformations, this set is a permutation. Okay, you want to say that this map which maps every element, the right multiplying map, that is a permutation. Map is a permutation. Permutation. Okay. Permutation means it's a bijection. It maps every element to a different element. Okay. So this is what this is called Cayley's theorem. Cayley's theorem in the case of the case of groups. Okay. Now such they have multiple names. Cayley's theorem, the case of groups. Okay, it's also called class Wagner Preston theorem in the case of inverse semigroups. So basically what it says is that every semigroup is isomorphic to a sub-semigroup of transformations. Okay. Now in the case of groups, that sub-semigroup of transformations actually happens to be a set of bijections. Right? In the case of inverse semigroups, it so happens to be a set of partial bijections. Okay. Yeah, I mean, I'll leave it to you to to complete the proof, the details of this proof. I mean, it's not that complicated. It's very simple. Okay. Okay. All right. Okay. Okay. So today we learn what is morphisms of subsemigroups, morphisms of semigroups. What is subsemigroup? Now let's get into semigroup congruences. Okay, so let S be a semigroup. Okay, let tilde be an equivalence relation on S. Okay, so I have a semigroup S, and tilde is an equivalence relation on the set of elements of S. Tilde is a congruence if A tilde B implies X A Y tilde X B Y. Okay, what does this mean? This means that this equivalence relation is in such a way that it respects the multiplication operation of the semigroup. Okay, so for instance, example, let's imagine tilde is a congruence relation. So let's imagine A1 is tilde A B1, and A2 is equivalent to B2. Then A1, A2 will be congruent to A1, B2. Similarly,
B1, B2.
Right now the definition I gave is that A is A tilde B, then XAY is tilde XBY. Yeah.
Okay.
Okay.
But actually, in this case of semigroup, we don't
Yeah.
have an X, right? Currently, a Y, sorry.
Uh, for
Like
all
right now,
x, y in.
the, so for monoids, it is okay to say XAY is congruent to XBY because one of them
Yeah,
can
yeah,
be
yeah.
the
So
identity.
xay is in S1. Okay. Xay is in S1.
Okay.
Okay. So let me rephrase my definition. So let S be a semigroup. Tilde, let tilde be an equivalence relation on S. Then tilde is a congruence on S. Okay. So that's understood. Tilde is a congruence on S. If I have A tilde B, it will imply that xay tilde xby for all xy in S1. That means x and y can be identity also. Okay, so what does this mean? I hope it is clear what I mean. Uh, so what does this mean? That means that if, for instance, if a1 tilde a2, then this will imply that first of all a1b tilde a2b. This is given because I can take x to be 1 and y to be b. Okay. Similarly, this will imply that if a1 tilde a2, this will imply that b a1 tilde b a2. Okay. Okay. And what about a1 tilde a2 and b1 tilde b2? Can I say that a1 b1 is tilde a2 b2 according to this equivalence relation, congruence relation? I think we can. Yeah. Why? Because a1 b a1 b1 tilde a2 b1 from this relation, from this, and a2 b1 tilde a2 b2 because b1 tilde b2 and I can left multiply by a1, so a2 b1 tilde a2 b2. Now since these two are equivalent and a2 b1 and this and this are the same, I get that a1 b1 tilde a2 b2. Okay.
But have we included transitivity in the relation we defined just now?
Yeah, tilde is an equivalence relation.
Oh, okay, okay.
Okay. So basically what I mean is that what happens is that I have a semigroup S. Okay. And I have a part an equivalence relation. What does an equivalence relation mean? It means a partition of S. Okay. So I have an equivalence relation. So tilde on S will be, tilde will partition the set of elements in S to different compartments. Each of them is an equivalence class of S. And what does this condition mean? The whatever I just proved is that this condition, what is this condition? A tilde B implies xay tilde xby for all xy in S1. What does that mean? That means that if I take an A1 here and a B1 here, if I take an A1 and A2 here and a B1 and B2 here, okay, and I look at A1 B1, if A1 B1 so happens to be here, then A2 B2 will so happen to be the same equivalence class. That's what I just proved now. Okay, because A1 A2 A1 tilde A2 implies A1 B tilde A2 B, A1 tilde A2 implies B1 BA1 tilde BA2, and from this condition I want to show that actually this I can see the congruence relation to be such that when I multiply two equivalence classes, I'll get another equivalence class. Yeah, when I multiply a1 b1, if it is here, then a2 b2 will be here. Okay. So therefore, the idea is that I can actually consider, we can consider S slash tilde, that means the equivalence class to be just one point. Okay. S slash tilde to be a semigroup. Okay. Who was in who is somebody in MSc? Can you tell me if you understood this or?
Yeah.
Yeah.
Okay. So we can consider S slash. So if tilde is a congruence on S, I can actually consider the equivalence classes. I can make a new semigroup, which is like the elements of the new semigroup are equivalence classes of the whole semigroup, and the product operation is actually, if I multiply two equivalence classes, I'll get a third equivalence class. Okay, and this semigroup S slash tilde is called the quotient of S with respect to tilde. Okay. Okay. We will see two important applications of this notion, congruences and quotients. Okay. Now let's prove one example, one case one. Case one. Quotient by homomorphisms. Okay. So let's imagine I have a morphism S to T. Okay. There is a morphism from S to T. I'm going to define equivalence relation tilde phi is the nuclear. This congruence, I'm going to define a new. So whenever I have a morphism from S to T, let's call it phi, I'm going to define an equivalence congruence relation tilde phi. Okay, I'll define what is this congruence relation. It's called the nuclear congruence of phi. Okay, what is that? I'll say A is tilde B for A, B in S if phi of A equal to phi of B. What is going on here? So this is S, this is T. Imagine T has only 3 elements. Okay. So now what happens is that I can partition the set of elements of S to 3. Each section will map to all the elements which map to this element of T. Okay. So if I have a morphism from S to T, then I can define an equivalence relation on S. What is this equivalence relation? Two elements of S are equivalent if they map to the same element of T. Now we have to prove that this is a congruence. How do we prove that this is a congruence? Clearly, it's an equivalence because it partitions the elements of S into 3 portions. Yeah, and every equivalence relation corresponds to a partition, and similarly vice versa. Every partition corresponds to an equivalence relation. So this is an equivalence relation because it partitions the set S. Now we have to show that this is actually a congruence. How do we show that it's actually a congruence? To show that this is actually a congruence, let's take 2 elements, X and Y, A and B. Okay. So to show that tilde phi is a congruence. Okay. So let A is congruent to B. Okay. That means that phi of A equal to phi of B. Now what should I prove? I should prove that we should prove XAY is congruent to XBY. So if I take for XY if I take elements X and Y from S1, okay. So the idea behind, I hope the idea behind saying S1 is clear by now. The idea is that I may not want to multiply by some element on the left and right all the time. So that's why I just take it to be, okay, sometimes you can just take it to be identity. That means that you don't have to multiply on the left or on the right. That's what this means. Is this clear, what I just said?
Yeah.
Okay. We should prove that XAY is tilde XBY. How do I prove that? So I should prove that phi of XAY is equal to, suffices to show, the phi of XAY is equal to phi of XBY. Because if phi of XAY is equal to phi of XBY, then it means that they are equivalent with respect to the nuclear congruence. Yeah. Now, what does this mean? This is equivalent to phi of X times phi of A times phi of Y, and this is equivalent to phi of A times phi of X times phi of B times phi of Y. Now these are equivalent. Why? Because phi of X is same as phi of X, phi of A is same as phi of B, and phi of Y is same as phi of Y. So therefore, these two terms multiply to the same element in T. Yeah, because phi of A is same as phi of B, the same element. The other two elements are the same. So therefore, uh, these two elements multiply to the same element in T. Therefore, this tilde is a congruence. Okay. All right. So therefore, whenever we have a morphism from S to T, actually I have a congruence relation on S. It actually forces a congruence relation on S. And therefore, I can quotient this semigroup S with respect to that congruence relation phi. Okay. And there is an important theorem, which is a standard theorem. It's called first isomorphism theorem. What is first isomorphism theorem? Okay, first isomorphism theorem. Let S to T be a let's call it surjective morphism. What is a surjective morphism? What is a surjective morphism? Can somebody guess what is a surjective morphism?
Morphism which is a noun to function.
Yeah. So that means that every element of T is mapped by some element in S. Okay. Surjective morphism. Okay. And let's call it phi. Phi from S to T. Phi is surjective morphism. Then what happens? So I have S here, I have T here, and I have a surjective morphism from S to T. Now I have the congruence relation tilde phi, which is induced by this morphism on S, and I can quotient with respect to that congruence relation. I can quotient S. What is this? What is this? This is a semigroup of equivalence relations with respect to the congruence relation phi. Sorry, semigroup of equivalence classes. Sorry. Yeah. Okay. And what is this? There is a natural morphism from S to S slash tilde phi. What is this natural relation? Which maps every element in X to the equivalence class of X with respect to the congruence relation phi. Okay. So when I talked about this congruence relation, there is a natural morphism from S to S slash tilde. What is that? It maps every element to the corresponding equivalence class of X. Okay. And you can actually show that this is actually a surjective morphism in the sense that every element in every equivalence class is mapped by some element, and this is actually a morphism. Yeah, morphism of semi-groups. Okay. Okay, so now what is remaining is that the first isomorphism theorem says that if I have a morphism from S to T, okay, and then if I look at the nuclear congruence and quotient with respect to that congruence, then I get another morphism from S to S slash delta phi, and there exists a morphism from S slash tilde phi to T. Let's call it pi prime. Can somebody guess what will be this pi prime? Not Dhruv, not any BSc student. I wanted to hear from MSc students. Saina?
Yeah.
What can be this? What is this pi prime? Like, is it an isomorphism or a homomorphism or a just?
Yeah.
Yeah.
Yeah, it can be a isomorphism. Like in
Yeah.
each equivalence class, take any element, and the phi of that element.
Yeah.
Uh,
So the first isomorphism theorem says that it is an isomorphism. Okay. So exercise state the first isomorphism theorem and prove it. Okay, so you have to specify what is S, what is T, what is phi, what is pi, what is pi prime, etc. Define what is each of them and prove that this thing holds. Okay, for Friday. I'll stop there. Okay. Thank you. Can the MSc students stay back for 2 minutes? I just want to ask you privately. The BSc can leave.
Thank you, sir.
Yeah, thank you. MSc and PhD only will stay back. Yeah. Others, please leave BSc. Yes, so did you understand what was happening today? How many MSc students do we have? Hello?
Yeah.
About
There
9,
are
I think.
5, 6, no,
Six? Okay.
6.
All right. So was it too hard today?
No, sir.
No,
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 it
no.
was fine.
Just fine?
yeah, it was
Yeah.
fine.
Okay. So you have to do the exercises. I'm going, yeah. So, yeah. So initially there are some groundwork we have to do. I think from now on, things will start getting slowly improving. We have to do this initially. Once you get the flavor of this thing, it will be fine. All right. Do the exercises, and I'm mostly teaching from chapter 2. You can look at the chapter 2. I'm skipping a lot of things also, but many of the things what I'm saying is there. So, yeah. All right, then. See you on Friday.
Yeah, so I think basically we have seen all these things before, but it's been a long time. So we just need to brush things up. So that is what we have to, yeah.
Okay. You are BSc or MSc?
MSc. So I did my BSc from CMI. So I have seen
Okay.
most of these things.
Yeah, you have seen most of these things in terms of books. That's why I know that you have seen this already, but I don't want others to feel that that I'm skipping over the details. All right. Okay, then see you on Friday.
Okay. See you.
Okay.
Bye.
Thank you, sir.
Thank you.
Thank you, sir.